In this video, we're going to talk about the use of dummy variables to represent qualitative variables. A qualitative variable is one that is a characteristic that's either true or false, unlike quantitative variables where the values take place on some sort of numerical scale. So examples of qualitative variables would include things such as gender, race or ethnicity, geographical location, the level of educational attainment, for example, whether you have a high school degree, an associate's degree, or a bachelor's degree, or whether or not a particular government policy is in effect or not. The way we represent these qualitative variables is by creating what we call a dummy variable, which is assigned to have the value of 1 if the characteristic is present for that observation, and 0 if the characteristic is not present. So in the data set that you're working with, let's say if you're working with an Excel spreadsheet, a dummy variable would be a column consisting of 1s or 0s. If it's 1, it means that characteristic exists. If it's 0, it means it does not apply for that particular person or for that particular observation. Let's consider a really simple example of this, an earnings equation, where we have earnings as just a linear function of experience, plus we include a dummy variable that equals 1 if the person is male and 0 if the person is female. Let's consider the implication of this dummy variable on this equation. For males, the dummy variable is 1, and we can substitute a 1 in place of it, and we get an earnings equation that has an intercept of beta 0 plus beta 2, because again, it's beta 2 times 1 plus beta 1 times experience. If the individual is female, the dummy variable takes on the value of 0, and the earnings equation is just equal to beta 0 plus beta 1 times experience, plus an error term for both equations. So what that dummy variable is telling us is how the intercept of this regression changes when the dummy variable is true. In this case, it would tell us the amount by which the male intercept is either higher or lower than the female intercept, and the difference between those two intercepts would be equal to the estimated value of beta 2. The diagram on the right illustrates that sort of relationship. Here, we're assuming that beta 2 is positive, which unfortunately is something that we still tend to observe. In this case, female earnings would be represented by the equation with the intercept of beta 0. The male earnings equation is represented by the equation with the intercept of beta 0 plus beta 2. And when we estimate this equation for the entire sample, the way we test for a gender difference in the intercept is just by testing the null hypothesis that beta 2 equals 0. If we can reject that null hypothesis, that tells us there's a statistically significant difference between male and female earnings. Or more precisely, the male intercept for the earnings equation is significantly different than the female intercept. In a dataset that is derived from a relatively old dataset from the National Longitudinal Study of the High School Class of 1972, this is an earnings equation. We estimate for the entire sample. So we have earnings would be equal to 11,666 plus 127.38 times weeks of work experience plus 8,873 times a dummy variable. And what that's telling us is that in this equation, the female intercept would be $11,666. The male intercept, though, would be 11,666 plus 8,873. And if we wanted to test whether there's a significant difference, we would just perform a t-test on the coefficient multiplying the dummy variable. And that's basically all you need to do to test for a difference in the intercept of an equation. We can also use a dummy variable to test for the difference in slope. And we do that by combining the dummy variable with the concept of an interaction term that we discussed earlier in this chapter. Since we're only testing for a difference in the slope, we create a new equation with the intercept of beta 0, and then we have beta 1 times experience. But now we include another term, which is the dummy variable times experience. And if the individual is female in this example, DI would be 0, and it would be just beta 2 times 0. But if the individual is male, it would be beta 2 times 1 times experience. And just by writing it out for both males and females, what we would get is for individuals that are male, the earnings equation would have an intercept of beta 0 and a slope of beta 1 plus beta 2. If the individual is female, the earnings equation would be beta 0 plus beta 1 times experience. So in this case, beta 2 would tell us how the slope changes in the case of females versus males. In particular, beta 2 would be a measure of the difference in slope that occurs when the person is male. And again, to test for a significant difference in the slope, all we would need to do is perform a t-test on the parameter beta 2. Here's a diagram illustrating the difference. Under this specification, we're assuming the intercept is beta 0 for both, and what we're doing is we're testing for the slope difference. In the case of females in this sample, the slope is just equal to beta 1 because the dummy variable is 0. In the case of males, because the dummy variable is 1, the slope would be equal to beta 1 plus beta 2. So again, beta 2 is just the difference in the slope. You might wonder whether we could test for a difference in both the intercept and the slope, and that's actually going to be the topic of the next video. So be patient, and if you really want to check that out, move ahead and watch the next video as soon as you finish this one. So now though, when we estimate that equation, again with the same sample from the National Longitudinal Study of the high school class of 1972, we get this equation, which tells us that in this case, female earnings increased by $57.4 for every week of work experience over that entire sample, but the male earnings increased by 57.4 plus 134.16, which is again a pretty large difference. And here I have included the t-statistics, and we find that that t-statistic of 20.07 is going to be highly significant. So this is telling us that there's a significant difference in the slope of the earnings equation between males and females in that sample. One thing we should note is that normally we don't include just one dummy variable in most regression models. Often, we'll use sets of dummy variables to capture groups of qualitative variables. For example, if we're looking at the impact of race or ethnicity, we might have many different categories, such as Black, Hispanic, Asian, Native American, and so forth. And we might have a dummy variable for each of those. Similarly, if we have different geographical regions, such as rural or urban, or northeast, south, west, and so on, and similarly for alternative levels of educational attainment, where we might have people who did not complete high school, people with a high school degree, people with an associate's degree, people with a bachelor's, a master's, PhD, or other alternative levels of educational attainment. In each of these cases, there is generally one dummy variable for each category. One of the things we have to do, though, when we try to compute this, is we have to exclude one of those categories, and then each of these coefficients would be measured compared to the excluded category. Notice in the example we talked about right before this, there were two potential dummy variables, male or female. We only included one of those, and in that example we talked about the dummy variable for males, but we interpreted that as being the difference compared to the excluded category, which was females in that case. We do the same thing in each of these cases. And the reason is, otherwise we run into something called the dummy variable trap. And the dummy variable trap is because if we include a dummy variable for each and every possible case, you'd essentially have a set of variables that all added up to one or a constant. And what would happen is we'd have perfect multilinearity between the set of dummy variables and the constant term. So we have to omit one variable from the set of dummy variables to prevent a perfect multilinearity situation. And we interpret the coefficients on each one of the variables as being the differential effect of that variable being present compared to the excluded category. Here's an example of that relationship. Suppose we specify an earnings equation which is quadratic in work experience, and we include dummy variables representing alternative levels of educational attainment. In this data set, educational attainment was coded as SC, which represents some college, which is 1 to 3 years of college, CD, which stands for a college degree, essentially a bachelor's degree, MA, which stands for an MA or an MS degree, and PhD, which represents either a PhD, law degree, or medical degree. Those were all lumped together into that one category. Notice the category that's left out here is a high school degree. And in particular, this was a study of the high school class of 1972, so everyone in the sample had completed high school. We didn't have any high school dropouts in that sample. So the excluded category here would be a high school degree. So we're looking at the differential effect of going beyond high school and getting some college, going a bit further and getting a bachelor's degree, and similarly for a master's degree or PhD, medical degree, or law degree, they're all lumped together in that one variable. And when we estimate the equation, we get something like this. The intercept for the excluded case of a high school degree would be beta 0 because each one of those dummy variables is 0. But if we look at the impact of having 1 to 3 years of college, the intercept would be beta 0 plus beta 3. If we look at the impact of having a bachelor's degree or college degree, in that case a CD variable, that would have an intercept of beta 0 plus beta 4, and so forth. So this equation allows us to represent the earnings profile of individuals with alternative levels of educational attainment, and each one of those dummy variables represents the impact of that level of education compared to the excluded category of a high school degree.